Hi, my name is Stephanie Gorski and I'm the developer of SquirrelJME. This is a Java ME8 virtual machine that is making sure that ancient cellular Java platforms are being preserved. I do really enjoy platforms at the lower level, and I have worked on compilers as well. If you have Twitter, there's a Twitter for the project, and I also have a personal Twitter as well. All of my information is here. This is what I will be presenting today. Why preservation is important for J2ME/Java ME. Why cannot we just use a desktop JVM and run software on it? Why write a JVM? Unique challenges to developing Java virtual machines and everything you can get away with because you're allowed to. What SquirrelJME is and how it intends to solve these problems. Q&A will follow at the end. And with that, let us continue. Is it J2ME or Java ME? J2ME is Java ME, and Java ME is sort of J2ME. In the past, Sun made everything Java start with J2, which stood for the Java 2 platform. You would get J2SE 5.0, which is Java 2 Standard Edition 5.0. These days, it's just called Java SE 8 or Java ME8. Just like how Windows NT 5.1 is Windows XP and Windows NT 10.0 is Windows 10. To keep everything consistent, Java SE and Java ME will be used going forward. Preservation is important. Why preservation is important for Java ME? Why cannot we just use a desktop JVM and run software on it? Why write a JVM? Java ME is very old. Java Specification Request, JSR 30, started development in 1999. Defunct companies such as AOL and Symbian were considered part of the expert group for the standard. You do not see them around today. Java ME8, JSR 360, which SquirrelJME implements, is only from 2014 and took 2 years to develop. Java is constantly evolving. Java 18 will be released in a few months. There are dozens upon dozens of different devices with their own APIs, and some are copied by other manufacturers as well. Some are even specific to a single region. Some of these services are gone, never to come back again, especially with the end of 2G and 3G. There are countless troves of useful, creative, and shelfware applications that exist. Because of all this, you can't really rely on existing Java virtual machines such as Java SE or Android to implement on top of. In 10 years, it might not even be possible to run older versions of Java anymore outside of virtual machines, or perhaps even emulators running older versions of Windows, for example. There must be standalone virtual machines that are capable of running existing software that can keep up with the ever-evolving platforms and devices that they can run on. This is something that SquirrelJME intends to provide so that this history is preserved for future generations. As an aside, Java SE keeps changing. When it comes to desktop systems, Java SE keeps changing. Older APIs are being deprecated and removed, some of which Java ME can depend upon. These are APIs that you should never use today. Java SE and Java ME have a very little intersection anyway, so it does not really matter in the end. Requirements of the JVM itself are changing over time. Examples of this include verification of bytecode. Bytecodes are verified to ensure that they're not doing anything weird and exploitative. Also, everyone is no longer interested in supporting ancient Java that is not even being used anymore. So away it goes. The backwards compatibility of Java for software that has been around so long is not guaranteed, and there is a continual drive to evolve and remove the unused from the past in Java. Of course, this is something that is healthy for a language, and it has been seen in many others. Keeping the backwards compatibility to the extreme can add limitations and otherwise, which is one reason why generics in Java were implemented the way they were. That implementation of generics is why Java ME8 can have them without any issues. because they only exist at compile time. However, for other features of the language, it is not that simple, such as for method references and lambdas. These are additionally great features, but if Java concentrated on backwards compatibility to the extreme, they would not have been implemented or would be ultimately clunky. The more time that goes by, the more rugs that are pulled from underneath. Eventually, you'll run out of rugs, and what do you do then? You build something that is not going to change much. There are two major JavaME APIs that the vast majority of applications will use. The Connected Limited Device Configuration, CLDC, which is the core virtual machine and set of classes, and the Mobile Information Device Protocol, MIDP, which provides a UI framework so one can interact with said application. As mentioned previously, the first version of JavaME was released in 2000, and it would get a slow number of updates over time, with just one minor update to 1.1 in 2003. MIDP saw a major update with 2.0 in 2002, but the later MID 3.0 was a much-needed update that did not come out until 2009. If you remember history, the iPhone came out in 2007 and Android in 2008. This meant that JavaME, for the most part, was dead in the water, and that everyone wanted iOS or Android anyway. It was not until April 2014 that JavaME 8 was released, just 1 month after Java SE 8. JavaME 8 is really just an attempt at bringing the platform to the forefront again like old times, sort of, with embedded systems. However, I will note that the Raspberry Pi was released in 2012, and there was quite the wave in Internet of Things and other embedded devices such as the Intel Galileo, the MIPS Creator CI20, and others. So in reality, the refreshed platform was a bit too late when it came to things. JavaME in the past was still evolving and improving in the background, except chances are that you completely missed it. If you in the past developed for JavaME, here's what you missed when JavaME 8 came out. Otherwise, this slide might not make much sense to you. Brings the language up to date with Java 7 features such as try with resources, iterators, enhanced for loops, and actual enumerations. Adds support for generics, which are very useful. Java SC5's collection framework, no more using only vector or stack. A bunch of helpful methods for integer bit manipulation. Native I/O with the ability to read and write files without needing to use DCF. Byte, short, int, and float buffers. Channels, which are fancy input/output streams. So, as you see, although it was too late to bring back JavaME, these were very welcome additions that I do wish came sooner rather than later. Of course, with iOS and Android being out there so much today, it was too little too late. However, in terms of SquirrelJME, it is easier to work with as I am not limited to the more ancient JavaME 1.1 or otherwise. In terms of specific functionality provided by APIs, there are many that are available. You have everything from 2D graphics, 3D graphics, sensors, networking, sound, music, media, and more. Of course, the majority of these provide a different class structure compared to others, which means that you would have to actually modify code to use them. So essentially, they are not a drop-in replacement in any way. Another issue would be that a device need not support these, and in such case, there is nothing you can really do unless you want to write your own wrapper layer over an existing API or port your code base to it. From this, you might not really say that JavaME has a limited platform in terms of which APIs are available, although the hardware it runs on is limited itself. Ultimately, though, due to the vast number of APIs that are actually available, it will take much time and work to make sure they are implemented correctly and preserved accordingly. The wheel was meant to be reinvented. Some vendors even decided to reinvent the wheel and not use standard JavaME APIs because standards were meant to be broken, correct? The majority of these APIs are carbon copies of existing standard JavaME APIs, just with different names. Mostly stems from JavaME in the early days being limited and the slow pace of new standards being codified. A vendor was free to do their own thing in the interim. Some examples of this: Applix JBlend for I/O, UI, graphics, audio, video, and networking, SKT WP, applications, UI, graphics, video, and networking, NTT Docomo, known as iMode/iApply, applications, UI, graphics, audio, networking, and storage. Especially with JBlend, WP, and iMode, all of these APIs implement their own user interfaces, which, although similar to MIT-P, have a different set of classes for them. In effect, these APIs are built on Java, but are effectively incompatible clones with APIs that have already been proposed and adopted by the Java community process. Take an example of Windows and Linux. There are file system handling APIs in C, such as fopen and fread. However, Windows itself has its own file system handling through the Win32 API, and Linux has it between standard C functions, but also special files on the file system, such as those in proc. This is essentially what JavaME is like when it comes to these various different APIs. Same fruits, but completely different taste and color. With every new API comes another API to replace it. Troves of software. JavaME has always been a platform where you can just do whatever you wanted when it comes to applications. You can get them from the store, or you can create them yourself. There is everything from media players, web browsers, games, calculators, compasses, reading, writing, and many more things. Most of the applications that exist have variants for specific devices or are locked to a single device due to specific APIs being used. If these APIs are not supported, they are not running at all. From this extreme freedom to do whatever you want, there are easily bunches of 100,000 applications, maybe 500,000, give or take a few 100,000. This is comparable to Windows or Linux, despite being a completely mobile and embedded-oriented platform. This freedom is pretty much how it got popular, with almost everyone using it in one way or another, even if they did not know they are actually using it. Even platforms such as Palmos, Pocket PC, and BlackBerry have their own Java implementation, even if not officially supported by Sun Microsystems. However, despite the amount of available software, it can be really hard to find, so if you knew how to write your own software, you would likely have to do as such. Goodbye, iMode. At the end of November 2021, the iMode service was shut down. Based on JavaME, this service, along with its APIs, were centered solely in Japan. It was a mobile platform for those living there. The vast majority of software is not preserved at all, and much of it is very possibly gone forever. For SquirrelJME, iMode will be supported API-wise. This is one major example of what is disappearing and what potentially may already be gone, and as such, it right now is a bit of a slow scramble to obtain software and learn about the platform. To be honest, for myself, I only first learned of this platform in 2021, which definitely goes to show how insulated this API was in the world. Naturally, it is another API, as previously mentioned, that reinvents all the wheels. Luckily, I have a number of books on the subject that give examples and working programs that I can use for testing. Additionally, they contain the API documentation itself. So with this, I am able to figure out how to implement the API accordingly. When it comes to these old APIs, they mostly exist in book form. However, books are nice to have. If this is not preserved, then it will be lost for good and may be hard to find again. It is much work, but the more time that goes by, the more arcane this becomes. Programs, APIs, and services taken for granted will one day disappear. Over the years, I have found and been informed of various APIs that I had no idea existed. And with this, I will be moving on to the next section. Starting from here, I will be switching between two different sections to make it easier to talk about a challenge and then how it is handled in SquirrelJME. This color will be the challenge, and the following slide will have a different color so that you should be able to differentiate between the sections. So to continue on, unique challenges. Unique challenges to developing Java virtual machines and everything you can get away with because you're allowed to. Nothing is off the shelf, stack-based virtual machines, annoying applications, and lack of native support. These are just a few of the challenges that exist. Of course, with any large piece of software, there are challenges around the design and implementation of it. So I suppose you can say that these are the ones I believe will be the most interesting to talk about today. As there is a bunch to go over, let us get started then. What is SquirrelJME? What SquirrelJME is and how it intends to solve problems on the way. Started development in February 2016 as an embedded Internet of Things platform. This is a Java ME 8 virtual machine which aims to preserve mobile and embedded Java platforms for the future. It intends to be 99.9% compatible with standard Java ME, to be cross-platform as Java is already, is open source and available under the GNU GPL v3, clean room design, and clean room reverse engineered. So as you can see, I have been working on this for a while. In fact, I started working on it 2 years after the release of Java ME 8. I really have a fascination with embedded in mobile platforms, tiny computers that can do many things. Over time, this has been something that has kept me going and kept me busy. It is something that I enjoy very well. Since starting the project, it has been quite the challenge, and there are many skills that I have improved upon since its inception. Although being clean room does increase the challenge, it does help to ensure that quality and that any laws are not being violated at all. However, before we continue, I must talk about the mascot for the project, since every project needs one. SquirrelJME has a mascot. He is a squirrel. His name is Lex, and his name is derived from Lexer, and definitely is not a reference to anything. A mascot is rather important part of any project and allows people to remember a project by a character, and oftentimes said character is a recognizable aspect of the project. So yes, SquirrelJME has a squirrel mascot. Now that this has been divulged, I shall continue. Nothing is off the shelf. Java SE normally has many libraries and frameworks that are available, such as Spring Framework. If there is a library you could use, it very likely is missing pieces or is too large and has unneeded functions for Java ME. Everything, for the most part, needs to be written itself. So yes, the thousands of libraries that are available for Java are just not a thing that you can use. Most of these libraries end up being really large and having many unnecessary bits or rely on features of the language to operate properly. If you develop often in Java, you might use something like Jackson to serialize and deserialize between JSON and HTTP API calls, and otherwise, in Java ME, This would not operate at all because it requires reflection to even work. So it has no idea what a class looks like and how to actually serialize it. Naturally, there are other ways to go about this, but this is just one small example of a taken for granted library that you cannot use. You might find a library that might work, but then find that it will not work out too well. You might find a library that seems to do something, but the part you need is actually not implemented or missing. So really, for such a platform like this that has not been developed on for such a long time, the availability of these libraries are just not there at all. Additionally, Java 16 is already out, and although Java 8 has been around for 8 years already, almost everything written today relies on features it first provided. Of course, this does not make a project impossible in any way. It just means more work to be done in implementing these. However, there are solutions to this. There are many similar APIs in JavaME. SquirrelJME will layer them on top of each other. Some examples: layering the WP and iMode UI API on top of JavaME's midP. All the various 3D libraries will be implemented on OpenGLES. This keeps it simple. It is no way fun to have 3 or more copies of very similar code you have already done the work for. If you remember the chart in the previous slide, you would find that there are a large number of APIs that are available to use, and that they are essentially carbon copies of each other. One important thing when working on a large project is not to have 3 or 4 copies of the same exact code, which does virtually the same thing, but they are written differently. So as stated before, one example is layering the different UI libraries on top of JavaME's standard LCD UI, which is within midP. This means that regardless of the platform your software was originally for, it will look and feel virtually the same as a pre-existing application. The same goes for networking and sound. For sounds, you already have one API that does it, unless of course you enjoy having a dozen different sound APIs. This also reduces the number of potential bugs that duplicate code would produce. Additionally, what if you were to fix a bug and you had to fix it 3 times? You would better off be fixing it a single time at once. This benefits any project, regardless of what it intends to do. iMode support. iMode applications are recognized. Apart from official SDK emulators, there are no other choices in running software. iMode preservation is still very much in the early stages. As you can see from the picture, these are the books that I own regarding iMode. Unfortunately, since this API existed solely in Japan, although as an aside, it was supposedly planned to be exported, but never really was. All the books except a few are in Japanese. This means using a translator to figure out what is being said and then deriving context from it. Luckily for me, there are books with examples in them, and one even includes a CD-ROM that I uploaded to archive.org, which contains demos and source code for all the software in the book. Having actual working examples and source code is very wonderful because normally, when you find any kind of software that existed on JavaME, it was obfuscated and made to be as tiny as possible. Luckily though, I can read Java bytecode just fine, so it's not a major deal breaker for me. When working on an emulator or simulator, you'll begin to just recognize CPU instructions and what they're doing. However, when it comes to iMode, although the process is slower due to a language barrier, it is still happening, and I hope to be able to run any program that is found in the future, despite there currently being none. At least with these examples, I can run something and not entirely have to guess otherwise. Java is a stack-based virtual machine. Java is primarily a stack-based machine. This means that you are essentially playing solitaire when executing the bytecode, if you were to execute it directly. It is slow interpreting the bytecode directly in this fashion, although it does work. Naturally, these are the slowest types of machines, but they are the simplest to implement and technically could operate on a principle of infinite memory, just like Turing machines. When running on these, time is essentially wasted putting values onto the stack to operate with. Luckily, though, Java at least has a register-like storage area for variables, although everything is still stack-based. If a virtual machine were to implement even basic stack caching, then the speed of the application would increase greatly, as stack caching is one of the best optimizations you can do on a stack-heavy machine. Thus, as such, pure interpreters for Java will always be slow, and this is the reason why. Of course, there are ways to mitigate this to not feel so bad, as long as those mitigations do not involve bytecode being executed in such a slow manner. Accelerating operations. Running everything within an interpreted environment is very slow and carries lots of overhead. Despite it working, if the operation is called many times over, then the overhead will quickly add up. Shell sort is used for any sorting operation, and the acceleration allows for faster array operations, faster graphic operations, and faster image loading. So SquirrelJME uses shell sort for sorting of any data, which is a very simple algorithm when it comes to sorting. Although it's not the fastest, most data that is going to be sorted on JavaME is going to be small data sets. Additionally, considering that the algorithm itself is up to 50 lines of code with comments, it does not take much space in terms of program size. The array operations that are accelerated are any operations that involve copying one array to another, and also as well filling an array with data similar to a memset. At least when it comes to quickly initializing or clearing data, this improves the responsiveness of the virtual machine. When it comes to rendering 2D graphics, these can get forwarded to the host environment for those operations to be performed. When the pure interpreter is used this way, it greatly increases the responsiveness and speed of applications drawing graphics. Additionally, if the host system supports hardware-accelerated graphics, then these operations could potentially be performed even faster. Related to graphical operations is the loading of images. Since some image formats are complex and involve a number of compression algorithms, such as PNG, this can reduce the time spent in the virtual machine for loading an image. Performing operations like these on a higher level can greatly improve the responsiveness of programs and otherwise. And if you can spend less cycles executing bytecode, the better. SquirrelJME comes with multiple virtual machines, of which currently they are used for testing purposes. There is the hosted environment, which utilizes an existing Java SE virtual machine running on the host system to execute all the various bytecodes and perform the API calls. However, the pitfall for this one is that eventually, as mentioned previously, Java is going to stop supporting versions this old, which means the time for this machine is very limited, unless you were to have an older Java install on your system. Springcode, on the other hand, is a pure interpreter, which is going to be the slowest virtual machine of these all. However, with the acceleration tactics previously mentioned, it sometimes is not that bad, depending on the application. Of course, the main purpose of this virtual machine itself is to have a verifiable reference implementation. So that way I know exactly how the code should run and what other virtual machines should emulate. From the both of these, however, there is a work in progress stack caching ahead of time compiled virtual machine. This one sacrifices execution cycles at the start to compile all the various bytecodes. However, it does result in much faster code. It is, however, complicated as compilers are, so it still requires more tuning and otherwise to bring it up to a well-running state. So from all of these machines, there will be a wide variety of choice when it comes to running applications in the future. Annoying applications, obfuscated applications, applications that hide errors and otherwise, completely ignoring them yet still failing, applications that just do weird things for some reason. As mentioned previously, the vast number of applications available on JavaME are obfuscated, mostly to reduce size. The obfuscation can make the code harder to read by removing meaningful variable names. However, Java itself does not perform any optimizations or otherwise on the bytecode, so it's easily translated back to source code, even if gibberish. However, even then, it can still be a challenge until you build the pieces back together. Another issue that is quite common are applications which catch exceptions and errors and then do nothing with them, which is bad practice. When working with vast quantities of software, finding everything like this is extremely common. Then you have the weird ones that do stuff such as reading an image and then just discarding the result for no apparent reason. Maybe something forgotten or as a sanity check? Luckily, there are ways to deal with this that have always been helpful. Fail fast and never no op. When a program hits incomplete code, you cannot rely on its state anymore. With a large number of APIs, you would have to directly follow and look at the code of an application to know which API it is calling. By failing on unimplemented code, it is easier to find points in the code that need implementing. You would be surprised by how much software changes when an operation does not fail, does absolutely nothing, or possibly uses a default value. Having an operation do nothing like this can make some software work, but it can break multiples of them in various unspecified ways. For example, say there is a program that calls a method which sets a value somewhere, but that operation is a no-op and the value remains at 0. If the application itself tries to read from that value, it'll still get whatever default value was there, and it's going to be confused about things. Another issue is that programmers love to make assumptions about things. So when given a garbage state, it will happily continue on thinking everything is okay. When there is such a large library to implement, there is increased surface area where this can happen, as you could be spending days trying to find out why an application enters a weird state. By forcibly terminating the program and admitting a stack trace of what happened, it is very possible to figure out what is being called and to implement that accordingly. Taking this iterative approach to API development has helped me much over the years and allows you to get a handle on the application and make sure it is running correctly as it is developed. It does take longer, but it is worthwhile and helpful. Custom testing framework. There is no JUnit or TestNG in JavaME. There are no real testing frameworks either. Such framework has to run on tiny virtual machines and be able to run anywhere your virtual machine is running. These tests must not only test an API, but the machine itself is implicitly tested as well. For the first 2 years I was working on SquirrelJME, I did not really have a testing framework. I would run the code and see what happens and verify that it worked. However, as time went on, this verification took more time to do, and some APIs being implemented were very complicated. So about 2 years into the project, I needed to write a testing framework. However, the main issue is the lack of availability. There was also a very specific requirement for it as well, since it was verifying the API and the virtual machine itself. Normally, when you write a test for a Java program, that test is ran on the developer's machine on the test framework. For SquirrelJME, that is not really possible. Sure, I can test if whatever API I implemented is correct, but beyond that, it gets more difficult due to the complexities involved. All of these tests need to be run on the virtual machine environment, which is how I know things are implemented okay. Of course, whenever there are bugs or otherwise, I do implement a test which tests a specific bug and then get that passing. Since all of these tests are automated, they can be run on every single commit and on every virtual machine. So I'd rather have a timeline or log of sorts when things go wrong. Proper testing has prevented a number of issues as well as making sure things are going smoothly. So do your best to automate whatever testing you can. It will save you plenty of time. Writing a debugger for Spring Coat. If all else fails, write a debugger. This greatly helps in fixing problems. You can see the stack trace in any thread. Can also see fields declared as well. Adding a debugger to Spring Coat was one of the best choices I ever made. Java has a standard debugging API called Java Debug While Protocol, or JDWP. This is a common API that most Java virtual machines implement. You can kind of think of it like GDB, such as how it can debug native applications and machines running in QEMU. The debugger that was implemented is fully capable at actually seeing what the virtual machine does while it's running. There is support for breakpoints and single stepping, both of which are very useful to have for anything that causes a thread of execution to be paused, whether by user, by breakpoint, or by stepping. The virtual machine itself will idle and wait for the signal to continue, so that when resuming a program, it is very responsive accordingly. The debugger is told of the various threads and tasks that the virtual machine is running, so that you can see everything in the thread view. There are also other various bits, such as being able to access fields and objects and classes, along with accessing details on arrays and strings as well. JDWP is for the most part rather straightforward, so I was able to implement the protocol and build it on top of the existing virtual machine I implemented. You can connect to the debugger using JDB, IntelliJ, your Eclipse, and run the program to debug it. Being able to use user-friendly debuggers has made finding and fixing issues much easier. If you're having trouble with specific code, I highly do suggest implementing support for debugging remotely. Now this is the final piece of the puzzle, running on native systems. A virtual machine needs to run on something, such as a hardware platform or an existing operating system. You will need native code, regardless of how you obtain and integrate it. It has to be fast, portable, and efficient. You will have to implement a platform for every operating system and piece of hardware you wish to support. How is this done? Being cross-platform, you need an API that works across all of them. Otherwise, you will be reinventing many wheels and having multiple copies of the implementation. Retuficode, a C port. This is a port of SquirrelJME written in C. As of this time, it is a work in progress. SquirrelJME is still standalone and 100% in Java, so this is just another option. It is capable of running on RetroArch and uses a portable backend. So Retriever Code still uses all the existing Java code in SquirrelJME without any changes. All of that code is joined together and packaged into a class library, which is used by the engine. SquirrelJME itself was designed to be portable, so it uses no native code in the Java library, but rather bindings to a native system, which is how it is able to be 100% in Java. By doing it this way, the platform itself is wholly independent and becomes separated into two separate parts. As long as Retriever Code is able to understand the package class library, execute the code, and provide that native layer, then applications will run just fine. The engine itself is designed to be very portable, so that way it can be adapted to different systems, assuming it makes sense to do so. For example, even within the engine, there are abstraction layers, for example, such as those which handle graphics and otherwise. This all goes along with the goals of reducing code duplication. With a simple native layer, this is achieved. Building compilers. The ultimate goal is to have SquirrelJME be able to compile itself to a target platform. The compiler is to use stack caching to improve performance. The AOT compiler will be used whenever a new application is installed. Writing compilers is quite the challenge, so although SquirrelJME already has Retriever Code, there is a work-in-progress compiler backend that is capable of turning Java bytecode into another machine language. These compiler efforts are effectively called summer code. The compiled code would have two implementations, one written in Java for testing and verification, and another in Retriever Code. So that way it is capable of running this faster compiled code. Naturally, the first target is a machine-agnostic language that is based on registers rather than the stack. So as such, it implements a stack caching compiler, which brings desired performance. Of course, eventually, I do plan to have it where the compiler is able to generate standalone executables that can run on native systems. These would include modern Windows, Linux, and Mac OS. By having this, SquirrelJME will be able to be completely standalone and not require an install of Java, which, as mentioned in the past, is a constantly changing platform. As a challenge and for something interesting to do, I intend to write some ports to older operating systems and hardware such as Mac OS Classic, Palm OS, and maybe even possibly the Amiga. These are not really practical for real-world use today, although it would be a good test to see how the compiler operates and how it can flow into various different systems. So yes, this piece of SquirrelJME is very complicated. However, it is something that will enable SquirrelJME to reach its goals. And with that, this is the presentation. Here's the information real quickly before the end of this. Also, before we go into questions, I do want to make a short dedication to Emily and Neer, who are not here today to listen to this. Both of you will never be forgotten, and I dedicate this project to you both. Thank you for watching and listening. I do hope you enjoyed this presentation. If you missed a chance to ask any questions, you can always ask on Twitter, either twitter.com/SquirrelJME or my personal Twitter, ZerShadowtail. You can ask on GitHub via the discussions board, or you can ask on the bridged IRC/Discord channels, IRC Libera Chat, SquirrelJME, and also on Discord. You can check the documentation for that link. and live broadcast finishes in 12 minutes, 50 seconds.
Yeah. All right. Let's go over the questions just in case we are live. But it's not switched. Okay, so it's going to switch. Okay, it switched.
Okay, that's good.
People just saw like 2 minutes of me. All right. All right, so we have some cool questions. You talk a lot about speed of emulation. Is it critical with modern laptops and smartphones being much smarter than 2000s era flip phones?
Yes, it is. Stack-based virtual machines are just so slow that even on modern systems, the Spring Code implementation, it can take like 1 to 2 minutes, right? And this is on like a 1 to 3 gigahertz laptop that I have, which is a ThinkPad. So, this is a Core i7, and with the stack-based virtual machine, it still takes like maybe up to like a minute to start. Before doing all the accelerated operations and stuff, it would take like 5 minutes just to start. And yeah, it's very slow. So stack caching and compile your code, and everything will just go like much faster.
Okay, but is it worth it at the end of the day?
Yes, it's worth it, because otherwise you'll be sitting there 5 minutes waiting for your program to start.
All right. Okay.
Yeah.
All right. Let's see. What was the trigger for you to work on this project? Is it like a piece of software you liked, or a phone you didn't want to let go of, or something like that?
So at least before this project, I tried writing an actual Java virtual machine, but for a desktop system. So that's like, 5,000 maybe classes just to implement. And it was kind of just like way over my head. So I do remember in the past, I used the flip phone stuff and I liked it. I mean, I did use Palm all the time, but I also had a flip phone that ran Java as well. So I was kind of like, running a virtual machine and implementing all the Java stuff is super interesting, but I'm like, this is way too big of a project for me to implement. So SquirrelJME is essentially just, scaled down a bunch. And yeah, I guess that answers that.
Yeah, all right. And a kind of like a follow-up question is because you chose to do it in Java, which is like, I don't know, like kind of like programming cannibalism or whatever. But so why Java? No, not something more system oriented.
Well, I kind of find Java interesting and I kind of like it, which I guess is not that common, but it is interesting. I know a lot of people say like Java is like super slow or it's complicated and stuff, but most of that comes down to like the actual virtual machine itself. Like there's the bytecode, and that bytecode itself is like extremely simple. So you could probably write like your own virtual machine, a basic one, and maybe like a few hundred lines of C, maybe. So yeah, it's still pretty simple.
All right. Let us see.
Some of the questions jumped around.
Yeah, we should give some feedback to the FOSDEM guys. Like, don't sort them on votes. It's like.
Yeah.
But how do you test the accuracy of your emulation? Do you have original hardware with apps?
I do have some original hardware lying around, although I can load software on it. But at least when it comes to Java and stuff, for J2ME and Java ME, is you'll have like thousands of devices, and 5 of them you could have 5 different phones, and they all run the program differently because of implementation bugs and how they kind of do things, right? So it's kind of like if you had an NES, instead of like the maybe few variations of the NES, you instead had like, 500 variations of it. and you're running an NES emulator. So you're like, well, variation 212 has this weird glitch thing, and we have to emulate it. So it's kind of like not feasible to do that. However, there is like a test emulator virtual machine kind of thing that comes with the development kit, and some software can run on there. But otherwise, for accuracy, I test it with the automated tests and basically reading the documentation and seeing whether the software works or not. I know it's not kind of like perfect to a device, but there's just so many devices that it's pretty difficult to do unless you like stick to just one.
Sorry. All right. Yeah. So there was a question earlier, and I think if you have any follow-up on that, somebody mentioned that I was about to type a question, but this slide mostly resolved it. I think this was talking about let's see, how does the architecture look so that you can share code between those 3 Java implementations, JVM implementations?
So I guess this needs to be answered. So SquirrelJME is kind of in 2 parts. There's the front end, which is the hosted Spring Coat and Summer Coat. Those are really just responsible for executing bytecode and whatever machine code, whatever that you have. And there's like a standard API that's defined, and that implements that API. But virtually all of SquirrelJME itself is written in Java. That gets compiled into a ROM, I guess you can call it that, and that contains all the classes. So that's the class library, and basically it's that Java code that's running. It just basically tells, hey, start at this point and this method, and then just start running. So pretty much the majority of it is in Java. It's just some, API bridging between whatever is running in front and then the stuff in the background. So I made it so it's just as simple as possible, So that has really helped, because it's kind of just like, we'll just use these, few dozen methods instead of, re-implementing all that stuff on the inside. Yeah.
Yeah, all right. I have a follow-up question, but let's stick to the audience questions first, and then
Yep.
So Anissa asks an interesting one, actually. So because Java ME 8 came out in 2014, did any device actually use it?
No. Apart from some testing devices. So this is by the time Android and iOS are all everywhere, and basically the answer to that is no. Nobody picked it up that I know of. So no companies used it, but they did release it for some platforms. So there's the FRDM K64F, the STM32429i eval, the Raspberry Pi, the Intel Galileo Gen 2, and the STM32F746G Discovery. And these were all essentially just test platforms. Like, they put them on there and be like, hey, we can run on the Raspberry Pi and we can run on this STM thing. And it was like, adopt our stuff, but nobody did that. So.
All right. So there's kind of like a follow-up question from Anissa as well. I'll go back to the other question after that. So was Java ME 8 retro-compatible? Yeah, backwards compatible, I guess. And if yes, yeah.
Yes, it was. So Java ME 8 is, of course, an extension of the older version. So there's J2ME. Anything that's on J2ME will run on Java ME 8. But so there are some language features in Java ME 8, such as like generics and stuff. The way that was implemented in Java is through like type erasure. So basically you'd have a list of, say, string. To the virtual machine, that would just be list. And the string kind of stuff was hidden by the compiler. So essentially, like the virtual machine is exactly the same as the older ones. It's just, just compiler magic is hiding, all the new fancy stuff. So, yeah.
All right. And I think the last question is, what's the hardest part of the JavaME API on the SquirrelJME and Java flip phone emulation?
Probably the hardest part is the ones that aren't really documented. So there's some APIs that have like no documentation, or it's kind of just like, there's like a single. So I look at the documentation to implement this stuff, right? Just and read all of it to see how it all fits in. But like, there's times where it's just like, sets the inhibitor to 7 or something, right? And it's just like, well, what does that even mean? And that's kind of like the more difficult parts, is like very vague sentences, or also contradictory documentation. Like at the start, it'll say, does this, and then there'll be another method down there that's documented, and it says does the other thing, which if you read both of them, it's just like, it doesn't make sense. These don't both fit into each other. And that's kind of just like the hardest part.
That's pretty interesting. I don't know. For some reason, I didn't imagine that would be undocumented. But yeah, okay, that's... I don't know. Anissa also mentioned something, and I'm going to mention it because it's so funny, because we were just talking about the exact same thing. Yeah. Because he said, I love this solitaire stack metaphor, right? We really love that part. It just made sense, and it was just a very good analogy, I guess. Or metaphor. I don't know.
There's also your question.
Sorry?
There's also your question.
My question. Yeah. So it's Java, of course. Yeah, 1 minute remaining.
Yeah. Oracle owns it. And they are red. So
okay, that's okay. Obligatory question. So, all right.
Yep.
So thank you very much for doing this.
Okay, thank you.
It was an amazing talk.
Thank you.
Yeah. Sorry.
Next year.
And see you again next year. Of course, is the hope.
Hopefully.
And inspiration. Thank you.
Well, thank you.
Thanks.
Bye. Thank you.
Yes.